Greetings to Dr. Zayed. We are from Home Group 4 and this is the presentation for phase 2 of the assignment. Here is our group members. This assignment, we were given an audio recording that contains high-pitched background noise. The objective here is to filter out the noise present in this audio recording. After designing and implementing the appropriate specifications, orders, and type of noise filter, the objective was successfully achieved.
Let's see how we plot the audio signal in the time domain plot. So firstly, we read the audio file and then we load the audio signal, and then we declare the parameters like length and time. Next, we plot the signal. So the plot displays the magnitude of the audio input signal in the time domain, where x-axis represents the time in second and the y-axis represents the magnitude of the signal.
So beside time domain plot, the frequency domain plot of the audio are also acquired so that we could study the range of audio frequency signal. So based on the given plot, it could be estimated that most of the noise are within the range of 500 Hz to 1 kHz, and this estimation will be verified based on the output result after the input signal is filtered.
So for the filter design, we propose to use an IIR filter. The type of filter is Butterworth filter. It is because Butterworth filter usually has a flat passband response, unlike Chebyshev filter, which usually will induce unnecessary ripples onto the passband region. So therefore, we chose Butterworth filter. We realized that actually this beep sound has a specific range of frequency, the operational frequency. So after a series of trial and error, we found out that actually the frequency is between 550 Hz until 950 Hz. Therefore, the cutoff frequency is we will design a band stop filter with a cutoff frequency of 550 Hz to 950 Hz with a frequency difference of 400 Hz. So the filter order is n equals to 3. Of course, by theory, the higher the order of the filter, the better the band stop response, which means it has a more steeper curve. But of course, by using a higher order filter, that means we will incur unnecessary high costs, especially in the design of the circuitry level. So therefore, that is not so practical.
This is a code for frequency response plot of the filter that plotted using Friis function. The frequency response plot of a filter provides information about how the filter affects different frequency in a signal, showing the magnitude and phase response of a filter as a function of frequency. The resulting plot shows the magnitude response of the filter in dB and the phase response in degree. As we are designing a band stop filter, the magnitude response shows a correct shape.
Next, for pole zero plot, as you can see in the MATLAB code, we use z-plane function to plot the pole zero figure. From the figure, it shows here all the poles are located inside the unit circle, indicate that the filter is stable. Stable filter ensure that the output does not grow uncontrollably over time and that the filter response is predictable. Also, you can see here, having 3 conjugate poles and 0 implies that the filter is third order. This plot figure also shows that the poles and zeros are closer to the unit circle, which can be said it have higher natural frequency and less damping.
The impulse response of a filter is the output of the filter when impulse signal is applied to its input. An impulse signal is a very brief signal that has a very short duration but high amplitude at one particular point in time. As you can see that we have used IIR filter to filter out the noise from the signal. This is the plot of the resulting filter infinite impulse response in time domain.
Moving on, we'll take a look at the plots of frequency component after filtering that are generated through these MATLAB codes. It can be clearly observed that after filtering, the noise that is suspected to be between the frequencies of 550 Hz and 950 Hz has been successfully removed, proving the effectiveness of our filter design in removing the noise.
Here you can see the part of the code that I use in MATLAB when I run it. You can see there are 2 graphs. The one on top is the original sound signal and the bottom one is the filter sound signal. The original sound signal has a much thicker x-axis compared to the filter sound signal. This shows that the filter sound signal has successfully filtered out the unwanted beep sound at the background of the original sound signal.
Now let's hear the difference between unfiltered and filtered audio.
0125.